Welcome to AskPrep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of physics, which is Bohr's atomic model, energy levels and spectral lines. Before Bohr's model, the atomic structure was largely based on Rutherford's nuclear model, which described the atom as having a dense nucleus surrounded by electrons. However, this model could not explain why atoms emitted light in specific patterns. Bohr introduced the idea that electrons move in fixed orbits around the nucleus, and each orbit corresponds to a specific energy level. Electrons do not spiral into the nucleus but instead remain in these stable orbits unless they absorb or emit energy. One of the most important aspects of Bohr's model is the concept of quantized energy levels. Electrons in an atom can only occupy certain allowed orbits, and each orbit has a fixed energy. When an electron gains energy, it moves to a higher energy level, and when it loses energy, it falls back to a lower level. This transition between energy levels is what leads to the emission or absorption of light. Bohr's model successfully explained the spectral lines of hydrogen. When an electron jumps from a higher energy level to a lower one, it emits a photon of light with a specific energy. This energy corresponds to a particular wavelength of light, forming distinct spectral lines. These spectral lines are unique to each element and are used to identify substances in both laboratory and astronomical studies. The applications of Bohr's model extend beyond explaining atomic spectra. It played a crucial role in the development of quantum mechanics, which describes the behavior of particles at the atomic and subatomic levels. Spectroscopy, which relies on the principles of Bohr's model, is used in fields such as chemistry, astrophysics, and material science to analyze the composition of substances. Although Bohr's model was a major advancement, it was later refined with the advent of quantum mechanics. Modern atomic theory describes electrons as existing in probability clouds rather than fixed orbits. However, Bohr's concept of quantized energy levels remains a fundamental principle in physics and chemistry. Bohr's model also helped explain why atoms do not collapse. According to classical physics, an accelerating electron should continuously emit radiation and eventually spiral into the nucleus. However, Bohr's theory stated that electrons in stable orbits do not emit energy, thus ensuring atomic stability. The impact of Bohr's atomic model extends beyond just hydrogen. It laid the foundation for further advancements in quantum mechanics and the development of more sophisticated models, such as Schrödinger's wave mechanics and quantum field theories. Today, the understanding of energy levels and electron transitions is crucial in explaining chemical bonding, laser technology, and semiconductor physics. Bohr's insights also revolutionized astrophysics and nuclear physics. The concept of quantized energy levels is applied in studying atomic spectra of stars, helping scientists determine their composition and temperature. Similarly, nuclear energy levels play a key role in fission and fusion reactions, which power nuclear reactors and the sun. One of the most fascinating aspects of Bohr's model is its explanation of spectral lines. When an electron absorbs energy, it jumps from a lower energy level to a higher one. This process is known as excitation. However, this excited state is unstable, and the electron soon returns to its original energy level. As it does, it emits energy in the form of light. The emitted light appears as distinct lines when passed through a prism, forming what is known as the atomic spectrum. Each element has a unique spectrum, much like a fingerprint. This discovery allowed scientists to identify elements in distant stars and galaxies by analyzing the light they emit. The concept also played a key role in the development of quantum mechanics, as it showed that energy levels in atoms are quantized rather than continuous. Bohr's model was initially applied to hydrogen, the simplest atom, and it successfully explained its spectral lines. However, as scientists explored more complex atoms, they realized that Bohr's model had limitations. It could not fully explain the spectra of larger atoms or the fine details observed in spectral lines. This led to further refinements in atomic theory, eventually giving rise to quantum mechanics. Despite its limitations, Bohr's atomic model remains one of the most influential contributions to physics. It provided a crucial step toward understanding atomic structure and revolutionized how we think about matter at the microscopic level. The idea that electrons occupy discrete energy levels is still fundamental in modern physics and chemistry, influencing technologies such as lasers, semiconductors, and even medical imaging. The impact of Bohr's model extends beyond theoretical physics. It laid the foundation for practical applications in spectroscopy, where scientists analyze the light emitted by substances to determine their composition. This technique is widely used in chemistry, astrophysics, and forensic science. In addition, the concept of quantized energy levels is essential in understanding chemical reactions. The way atoms interact, form bonds, and release or absorb energy in reactions is deeply connected to the arrangement of electrons in energy levels. Bohr's model provided the first real insight into these processes, paving the way for modern quantum chemistry. Despite its success, Bohr's model has limitations. It primarily explains single-electron systems like hydrogen but falls short for more complex atoms with multiple electrons. The introduction of quantum mechanics provided a more comprehensive framework, incorporating the wave nature of electrons and probability distributions rather than fixed orbits. Understanding Bohr's atomic model is essential for grasping the behavior of atoms and the nature of light emission. It provides insights into how elements produce their unique spectral lines and how energy is absorbed and emitted at the atomic level. As we conclude, Bohr's model remains one of the key stepping stones in atomic physics. It helped bridge the gap between classical and quantum theories, and its impact continues to be seen in scientific research and technological advancements. Thank you. This is AskPrep, your guide to mastering NEET preparation. Let's decode complex topics and simplify your journey to success.